Hey everyone, I am so excited to have you here today. We're about to take a really fascinating journey through the history of software deployment. If you've ever wondered exactly how we went from massive, clunky server rooms to modern, lightning-fast application packaging, well, you're in exactly the right place. So let's just jump right into it.
Here's a quick look at our roadmap for today. We'll start with dependency hell, move through the physical server era, the virtual machine shift, the container breakthrough, look at why Docker changed everything, and finish up with the real value.
But before we even look at the tech itself, we have to start with the core problem. It's honestly probably the oldest, most universal frustration in all of software engineering. Why does code work absolutely perfectly on a developer's laptop, but then completely fail the second it's deployed to production? The answer to that exact question is what drives this entire architectural evolution we're about to explore.
Section 1. The dependency hell problem. So, software is honestly so much more than just the code you write. When we think about deploying an application, we kind of just picture dragging and dropping a folder from point A to point B, right? But an app relies on this really delicate, almost invisible web of environmental factors. It demands a specific language runtime, like Node.js 22. It needs Postgres 17. It begs for highly specific OS libraries, environment variables, network configurations, the whole shebang. When an app fails on a new machine, the code usually isn't what's broken. The environment is just different. So the big question becomes, how on earth do we make these environments reproducible?
That brings us to Section 2, the physical server era.
Going way back, the earliest, most naive solution was to simply buy a giant physical server, install the OS, and just toss all your applications onto that one bare metal box. And yeah, this is a recipe for disaster. If you have an authentication service and a reporting service sharing the exact same environment, you are inevitably going to get library version conflicts, or, one app unexpectedly eats up all the memory, totally choking out the others, or even worse, a routine upgrade for one app cascades and completely breaks another. They're literally fighting each other for resources because there's zero isolation between them.
So you might think, okay, what if we just give every single application its own dedicated physical server? That gives us isolation, right? Well, yes, but it creates a massive new problem, and that is waste. For example, you might have App A using 8% of the CPU, App B using 12%, and App C using just 5%. That leaves a staggering 75% of your extremely expensive server hardware sitting totally idle. So sure, it solves the dependency conflict, but it creates an absolute financial and maintenance nightmare.
Section 3. The virtual machine shift.
Now, this was a massive evolutionary leap for the industry. Virtualization allowed us to run multiple virtual machines right on top of a single piece of physical hardware. Suddenly, App A, App B, and App C could all live on the same physical server but act like they were in completely independent environments. We've finally achieved strong isolation and way better hardware utilization, all without needing to buy a brand new physical box every single time we launched a new service. But as we know, every architectural choice has a trade-off. Virtual machines are fantastic for sure, but they are incredibly heavy. Every single VM requires its own complete, fully fledged guest operating system. Think about it. If you just want to run a tiny background worker, booting up an entire operating system just to isolate it is massive overkill. It means you're dealing with a huge resource footprint and agonizingly slow startup times. It became pretty clear we needed a lighter way to package our code.
Section 4. The containerization breakthrough. This next paradigm shift is really all about shedding that extra weight. In the heavy virtual machine model, you have your app, your libraries, and an entire bloated guest OS for every instance. But in the lightweight container model, you take your app and your required dependencies, and you simply share the underlying host kernel. You're completely stripping away the bloat of the guest operating system.
And here is the formal definition that really changed everything. You see, with VMs, we were thinking entirely in terms of managing machines. Containerization shifted our thinking to managing workloads. Instead of asking, how do I configure this server, engineers started asking, how do I package this application so it can run absolutely anywhere? It's process isolation rather than machine virtualization, a total game changer.
The practical engineering benefits here are just immense. Because you skip booting a full OS, your workloads start up at lightning speed. You get strong process isolation, universal portability across a developer's laptop or a cloud server, and amazing environment consistency. These are highly functional, real-world solutions to those exact deployment pains we looked at earlier.
Section 5. Why Docker changed everything. Okay, there is a massive misconception in the industry that we really need to clear up right now.
Docker did not actually invent containers. The Linux operating system already had the foundational technologies, things like namespaces and control groups, long before Docker arrived on the scene. But back then, using them felt kind of like arcane dark magic reserved for highly specialized systems engineers. What Docker did was simply give everyday developers an accessible, coherent mental model to actually use them.
The workflow became brilliantly simple. Step 1, you write a declarative Docker file, which acts as your machine-readable build instructions. Step 2, you build a versioned image from that file. And step 3, you run the isolated container. It was understandable, scriptable, and super easy to automate. Docker essentially won the developer ecosystem simply by making containerization easy and approachable.
Section 6. The real value of containers.
Let's look at the traditional server model again. In that model, systems mutate. You install a package, you patch a configuration manually over SSH at 2 a.m., maybe you add an untracked dependency. Over time, two servers that started out totally identical slowly drift apart. This is called configuration drift, and let me tell you, it is an absolute nightmare to debug.
So the really crucial point to take away from all this is that containers replace that drifting, mutating server with an immutable artifact. You don't log into a server and tweak things anymore. If you need a change, you build a new image version, you test it, and you deploy that new version exactly the same way everywhere. The real value is creating a highly predictable, defined, and reproducible environment that your whole engineering team can share. It finally, once and for all, eliminates the excuse of, well, it works on my machine.
We've seen how containerization brilliantly solves the packaging and isolation problem. But as we wrap up this explainer, I want to leave you with this provocative thought. What happens when your architecture scales up and suddenly you have 1,000 containers? How do they talk to each other? How do you monitor them? Where do they even run? Containerization is really just the first step. Running them at a massive scale is an entirely new challenge. But hey, that is an explainer for another day. Thank you so much for joining me and keep learning.